Hello and welcome to the Classical Assumptions video tutorial for ECON 4650. The objectives of this video tutorial are that you'll be able to create data to illustrate classical assumptions relating to the properties of the error term epsilon, to create data to illustrate classical assumptions relating to the sampling distribution of beta hat, and that you'll become familiar with running iterative or repeated regressions in R and extracting data from these. So for the classical assumptions video tutorial, basically we're going to go through and show some classical assumptions with data that we create, and we're also going to demonstrate some violations of those. We're not going to cover all of them explicitly in R. The text guide that goes along with this video is a complete review of them, but we're going to pick out a few and demonstrate them here. So the first one that we're going to work on is the second classical assumption that the error term epsilon I has a zero population mean, right? This is essentially saying that when the entire population of possible values for the stochastic error term is considered, the average value of that population is zero. Okay, and it's not likely to be the case in the case of a small sample size, but as the sample size approaches infinity, the sample mean is going to approach zero. Okay, and we can illustrate this idea with a simple regression we generate in R. So we're going to create the regression equation y equal to 50 plus x plus epsilon I. So in this equation, beta 1 is going to be equal to 0 because we are just illustrating the properties of the error term epsilon I. And we're going to create data for x by drawing 42 numbers from a uniform distribution from negative 50 to 50. So that's the first thing we're going to do. So we want to, first of all, we want to set the random number seed, and we have to do this each time that we create any random numbers in R. So we're going to say set.seed 200, and we're going to create our x variable as described. So we're going to say x is equal to, we're going to say 50 minus 100 times runif 42. Runif is a way of telling R to just grab 42 numbers from a uniform distribution from negative 50 to 50, with that last part being added on by that 50 minus 100 bit. So that is the deal. And if we look at a summary of x, we can look at the data that we've created there. And now we can generate numbers for y for beta 0 equal to 50 as we described before. And we're going to draw the errors from a standard normal distribution with the rnorm command. So again, we're going to say set.seed. We have to do this each time, or else the program will default to using some derivative of the date and time for the random numbers, and it won't be reproducible. So we say set seed, and y is 50 plus 0 times x plus rnorm, plus rnorm 42. And we can pull up a histogram of y here, and it's going to look normal. There shouldn't be any particular patterning here. Well, okay, this should be normally distributed, but in the next plot there's not going to be any patterning. If we plot x and y, then we see that since there's no relationship between x and y designated, we would expect to see this. There's not really a pattern. So we want to look at the errors specifically. So let's run a linear regression and pull the errors from that. So we're going to say model 1, that's what we're going to call it, and LM regressing x on y, so capital Y tilde capital X, and then we're going to plot this, plot density model, and then a dollar sign, and then residuals, right? So this is going to tell R to take it to plot what a density line of what of the model, and specifically out of model we are pulling residual data, so that's why there's a dollar sign residual. And if we hit enter and it didn't find it because I didn't write model 1. So make sure you identify we want model 1, and you hit enter. And if you compare this graph to the graph that is figure 1 on page 71 of the text, titled an error term distribution with mean of 0, this is kind of what we're looking at here. So we created the errors given the rnorm command, so it's not surprising that this looks fairly normal. But you may notice that it doesn't look, it's not perfectly normal or anything like that. So if we draw even more y values, we can get our hypothetical error term closer to the quote-unquote real unexplained parts of the y's in our regression. So let's draw from a larger sample. Okay, so we're going to say set.seed 200 again, and we're going to say capital X dot 2, so x2 as 50 minus 100 times runif 42. So we're actually not 42, sorry. We are doing 10,002. Okay, so we're drawing from a much larger sample size. And then set.seed 200 again. And we're going to do y.2 is 50 plus 0, so we're using the same model specification as before, times x.2 plus rnorm 10,002. Okay, and then let's run another model. We'll call it model1.large, and this model is going to be lm of y.2 tilde x.2. Okay, and then let's plot those residuals there. So we're going to say plot density model 1.large $sign again residuals. And before we hit enter, so glance at this graph, and then when we plot it, we see that given this, now we've drawn 10,002 sample size, we see that our error term distribution is looking much more normal. And you can see that, let's see, the mean of this distribution should be pretty close to 0. See model 1.large $sign residuals. So we're going to pull the mean of those. So that is a fairly small number. Compare that to the mean of the first model we did. Another fairly small number, but it's not quite as small. Or sorry, it's smaller, but it's not as close to 0, right? So that's what we're looking at here. As you increase the sample size, the mean of the residuals should approach 0, and this is what we're seeing here. So with the larger distribution, we had a very small number, or a number that's very close to 0, and with the smaller distribution, or with the smaller sample that we grabbed first, we had a mean that was very small but slightly farther away from 0. So moving on from there, the next classical assumption that we are going to demonstrate is the error term having a constant variance. Okay, so when this does not happen, the violation of this assumption is referred to as heteroskedasticity. Okay, so heteroskedasticity is when the variance in the error term is not constant, and what it ends up doing is inflating the estimates of standard error, so that though the estimators are still unbiased, they are not minimum variance. So it is an issue. And we can demonstrate this by generating data which has variance related to the explanatory variable. Okay, so we're going to change the code a bit so we can calculate the standard deviation of the error terms with non-negative numbers, which which is essential. So the first thing we're going to do is set a new x. This is going to be small x is equal to SEQ. So we're going to have R build a sequence from 1 to 42. The sequence is going to have an output length of 42. So tell R this. Okay, and then set your seed again so that we can reproduce these results. And then we're going to run a regression, or we are going to create some fitted y values with this. So we're going to say y, small y equal to 50 plus 0 times small x plus r norm, and then say length of x, comma, and then set the standard deviation, so SD equal to 0.1 times x, small x that is. So this is going to tell it to create fitted y values, but the error term is going to be drawn from a standard normal distribution, but with a standard deviation, which is going to change with x. So now we can create our model with heteroskedasticity. So we're going to say model dot het sched for short. It's a great name, and that is, so we don't need that. It is simply lm of y tilde lowercase x. Okay, and then we plot this. Say plot x, and then model dot het sched $ residuals. Again, we're using the $ to tell R that out of this model we want to pull certain data. So we want to pull the residuals data, and we want to plot it in comparison with the x variable. So if we plot that, we see here that the residuals are definitely not their variance is not constant. It is changing with the value of the x variable quite considerably. And if we want to look at like the absolute variance in the residuals, we can say plot x comma model dot het sched $ residuals and square it, and this will just show us the values. This is just another way to look at it. So there's definitely variance here that is increasing as there is a change in the x variable. And we can also run a summary of that model. Oops. And essentially we know that these parameter estimates would not, as we said before, necessarily be biased, but that the standard error would be larger. So that's just something to take into consideration as we're learning about heteroskedasticity. So the variance will no longer be as small as possible. And for illustration, we can run a similar regression equation without the error variance related to the x variable. And so then we can look at what that gives us. So again, we're going to say set.seed 200, and y.2 is 50 plus 0 times small x plus r norm length x, and again a comma, and then this time the SD is just going to be equal to 0.1, so it's not going to change with x. And then we're going to say model.normal is regressing this x on the new y2, so y.2 tilde x. And then if we plot the residual plot for that, let's say x model dot normal residuals again, then we'll see that as compared to our last model, the variance of the error term is not apparently related in some trend with x. So that's something to look at there. And again, we can, if we use the up sign to call up our last command, or the up arrow, we can add a caret and square that and look at kind of the absolute change there. So, and we can also run a summary of this, of model normal. And yeah, this is just, again, so now if this were some real data sample that we were looking at, we would be able to see that the well, we would essentially know that the standard errors were lower than they were before when we had heteroscedasticity, making our estimates minimum variance and hence blue, assuming the other classical assumptions were holding. So now we're going to talk about the sampling distribution of beta hat. Okay, so each different sample of data produces a different estimate of beta, and the probability distribution of these beta hats values across samples is called the sampling distribution of beta hat. And we know that an estimator beta hat is an unbiased estimator if its sampling distribution has as its expected value the true value of beta. So basically, if the expected value of beta hat, or the mean of it, is equal to the true value of beta, then it is an unbiased estimator. So let's illustrate this by looking at our first model. So let's run a summary of model 1, good old model 1. And we look here that the estimate for beta 1 hat here is equal to 0.004899, and that is pretty close to the true value, which we designated ourselves as 0. Okay, and if we changed our model to say that the true value of beta 1 was equal to 5, say by doing this, set.c 200, creating a new y2. So y2 is 50 plus 5 times x, big X, plus r norm 42. And then you could estimate the new model. So model 2 is going to be lm y2 tilde x. Looking at a summary of model 2, to get to the punchline here, you see that this estimates the slope parameter here, or beta 1 hat, at 5.004899, which is pretty close to the true value of 5. So we can repeat this experiment by telling R to draw values of y and estimate regressions, creating a sampling distribution of beta hat, basically by doing what we just did over and over again, like 1,000 times. But instead of typing it in 1,000 times, we're just going to have R run it and store the data, and we'll see what kind of distribution we get for the beta hats. So as you hopefully understand by now, the expected value or mean of the sampling distribution should end up being pretty close to what we tell it. In this case, we're going to tell it to be 0. To do this, we're going to set up placeholders for our estimates of beta, as well as their standard errors and t-values. And we're going to take 1,000 draws, estimate 1,000 regressions, and look at the estimates of beta which result. So in this example, as before, n is going to be equal to 42, k equal to 2. So n minus k is going to be 40, so 40 degrees of freedom. And we're going to repeat this exercise 1,000 times, and we're going to generate y values for beta hat 1 equal to 0, or beta 1 equal to 0 and the intercept equal to 5. And again, the error term epsilon is going to be drawn from a standard normal. So that was a whole lot of talk. Let's put it on paper here, or on electronic surface, whatever. So we're going to say set.seed 200 again, and we're going to tell R to create these placeholders. Okay, so what we're going to do is we're going to type, say, like we want a place for it to store the betas from the 1,000 distributions it's about to run. So we're going to say beta, and we're going to use the rep command, rep, 0 to 1,000. This is going to create a matrix that's big enough to hold all the data we're about to give it. R likes to put things in, like R likes to output information into spaces which are the right size. It gets excited and doesn't like it if you don't do that. So this will just save us time in some sense. So we did beta. Let's set up a placeholder for standard error of beta. Again, the same way. And for st of beta, for the t values, it's kind of a preview of what we're going to be doing in the next module. So rep. Excellent. And now we have to tell it what to do. So we're going to say for I, so for each time, think of I as being like each individual time it runs the regression. So for I in 1 to 1,000, so the first time to the 1,000th time, do the following, and put that squiggly bracket, oops, don't do that. So move to the outside of the paren and put that squiggly bracket, delete the one that is trying to close itself, hit enter, and then you can start typing your commands in nice and neat, just like it looks in the text from this module. So we're going to have it do whatever we're about to tell it 1,000, or from 1 to 1,000 times, right? So it'll do it 1,000 times. So the first thing it's going to do is estimate y. So y is 5 plus 0 times capital X plus R norm 42. Checking to make sure we did this right. Looks good to me. And we're also going to have it each time regress a model. So the model is going to be lm of lowercase y and x, capital X. Looks good. And we're going to tell it where to put the information. So in that little matrix we just created called beta for each I, so for each time it runs, it's going to dump the following information into it. Model. So it's going to grab information from the model, and specifically we're going to grab the second coefficient from the model, which is beta hat 1, or the slope coefficient. This is what we're interested in. It's a coefficient corresponding to the x variable. So that's great. And we're going to have it grab the standard error of beta. And in there it's going to put summary model. So out of the model summary it's going to draw this coefficient. This is a way of telling R to specifically go into the model output and grab the coefficient that corresponds to the standard error. Yeah, so that's what that's going to do. I'm just double checking to make sure we got this right. Make sure I spelled coefficients right. Looks like we got lucky. And then the t values it can calculate. So st beta for each iteration I will be equivalent to beta I divided by se beta I. Excellent. And then close it off with a squiggly bracket thing and hit enter. We didn't get any errors. That's excellent. If you got an error, don't fret. Just go back and type it all in again. And try not to, I guess, make the error. As you can see, I do it all the time, so it's not a crisis. So we just had it run this regression 1,000 times, and it grabbed a bunch of beta hats, and it pulled them out. So let's get a summary of what it got. Okay, so we're going to say summary of beta. Okay, excellent. So our mean of beta is a pretty small negative number. A very small positive number very close to 0. So that's a good sign, right? Because we expect the expected value, or the mean, of this sampling distribution for beta hat to be pretty close to the true beta, which we set as 0 right here. So that's great. And we can look at a density plot of our 1000 estimates of beta, because we like to do that, right? And let's give it a title to dress it up a little bit. Beta hats. Excellent. So there it is. And so that is, as you can see, that looks like a fair, like it. I mean, it looks close to a normal distribution, which is what we'd expect. And so finally, in relation to this mean of the sampling distribution discussion, I would like to talk about the standard error, because we're talking about the properties of the variance of beta as well. So basically, the larger your sample size, the smaller your variance will be, which will show up in your summary report as in the form of the standard error. And you can think of an estimator like a product, right? So the smaller the standard error, the better quality the product, or the better quality the estimator. So we can look at this by comparing. We can look at, if we look at a summary of model 1, you're looking at the standard error there for the beta hat 1 is fairly small. This was with our draw of 42. And then if you look at the summary of model 1 large, then you can see that the standard error is even smaller. So that kind of illustrates our point that as you increase your sample size, the standard error of the estimator will fall. It's important to remember that the standard error in general, which is equivalent to the square root of the variance of an estimator, is reflective of the sample size, as we just illustrated, of fundamental variance in the data. And in multivariate regressions, it's a function of how correlated the explanatory variables are. So you could try demonstrating this yourself by specifying a regression and running it with smaller and then larger sample sizes, and compare the standard errors of the estimates that result. Thank you, and that's the end of this video tutorial. Moving on, assignment 3 is available in Canvas in the classical assumptions module.